Imagine you're floating in space. Ahead of you is one of the most mysterious objects in the universe, a black hole. It's invisible. It emits no light. And yet it has enough gravity to trap entire stars. For decades, black holes have fascinated scientists and terrified science fiction fans. They're often portrayed as cosmic vacuum cleaners that swallow everything in their path. But what would actually happen if you fell into one? Would you be instantly crushed? Would you be stretched into spaghetti? Could you survive long enough to see the future of the universe? And what lies beyond the point of no return? Today, we're going on a journey into a black hole, from the moment you first approach it to the very edge of known physics. And the answer is far stranger than you might think. Before we jump in, let's understand what a black hole really is. A black hole forms when a massive star reaches the end of its life. After billions of years of nuclear fusion, the star runs out of fuel. Without the outward pressure from fusion, gravity wins. The star collapses under its own weight. If it's massive enough, the collapse continues until an incredibly dense object is formed, a black hole. The gravity becomes so intense that nothing can escape. Not even light. That's why black holes appear completely dark. At the center lies a region called the singularity, a point where matter is compressed to extraordinary density and our current understanding of physics breaks down. Surrounding it is a boundary called the event horizon. Think of the event horizon as the ultimate one-way door. Cross it and escape becomes impossible. No rocket. No spacecraft. No signal. Nothing can come back out. Now imagine you're in a spaceship heading toward a black hole. At first, nothing seems unusual. You might see a dark circular shadow against a field of stars. But as you get closer, something incredible begins to happen. The black hole starts warping space itself. According to Albert Einstein's theory of relativity, gravity isn't simply a force pulling objects together. Mass bends space and time. A black hole bends them to an extreme degree. Light from distant stars curves around the black hole. You begin seeing bizarre distortions. Stars appear stretched. Images duplicate. The black hole acts like a giant cosmic lens. You might even see light coming from behind it. Space no longer behaves the way your brain expects. The closer you get, the stranger reality becomes. Here's where things get truly weird. Imagine a friend watching you from far away. As you approach the event horizon, your friend notices something odd. You appear to slow down. Not because your spaceship is losing speed. Because time itself is slowing down for you. This phenomenon is called gravitational time dilation. Strong gravity slows the passage of time. Near a black hole, the effect becomes enormous. To your friend, your movements become slower and slower. Your signals arrive less frequently. The light coming from your ship becomes redder and dimmer. Eventually, you seem frozen at the edge of the event horizon. From their perspective, you never actually cross it. You simply fade away. But from your perspective, everything feels normal. Your watch ticks normally. Your heartbeat feels normal. You continue moving forward. And eventually, you cross the event horizon. Surprisingly, crossing the event horizon might not feel dramatic at all. At least not for certain black holes. If the black hole is extremely massive, millions or billions of times the mass of our sun, the gravitational differences at the horizon may be relatively gentle. There might be no sudden jolt. No wall. No warning sign. You simply pass a boundary in spacetime. Yet something profound has happened. Every possible path forward now leads deeper into the black hole. In a sense, moving toward the singularity becomes as unavoidable as moving toward tomorrow. You cannot stop. You cannot turn around. The singularity is now part of your future. Now comes the famous part. Spaghettification. Yes, that's the real scientific nickname. Here's why. Gravity gets stronger as you move closer to a massive object. If your feet are closer to the black hole than your head, gravity pulls harder on your feet. This difference is called a tidal force. Near many black holes, tidal forces become extreme. Your feet are pulled downward more strongly than your head. Your body begins stretching. At the same time, you're squeezed from the sides. Longer. Thinner. Longer. Thinner. Eventually, your body resembles a strand of spaghetti. Hence the name spaghettification. The process would be fatal. For smaller black holes, it could happen before you even reach the event horizon. For supermassive black holes, however, you might cross the horizon first and only experience these forces much deeper inside. Either way, the outcome is not pleasant. Let's imagine somehow you survive long enough to observe your surroundings. What would you see? This is where science enters uncertain territory. Inside the event horizon, spacetime is so distorted that our normal intuition fails. Light rays are dragged inward. Future paths point toward the singularity. The universe outside may appear distorted and compressed. Some theoretical calculations suggest you could witness external time passing rapidly. Stars evolving, galaxies changing, cosmic events unfolding at extraordinary speed. However, exactly what an observer would see inside a black hole remains an area of active scientific investigation. Our current theories provide clues but not complete answers. And that's because two of our greatest scientific frameworks begin to clash. General relativity describes gravity beautifully. Quantum mechanics describes the microscopic universe. But inside a black hole, both become important at the same time. And our theories stop agreeing. This leads us to one of the biggest mysteries in physics: the black hole information paradox. According to quantum mechanics, information cannot simply disappear. The details describing particles and physical systems should always be preserved. But black holes seem to destroy information. Anything that falls in becomes inaccessible. Even more confusing, black holes can slowly evaporate through a process known as Hawking radiation, proposed by Stephen Hawking. Over unimaginable timescales, black holes lose energy and shrink. Eventually, they may disappear completely. So what happens to the information that fell inside? Is it destroyed? Stored somehow? Encoded on the event horizon? Scientists still debate the answer. Some of the brightest minds in physics have spent decades trying to solve this puzzle. And we still don't have a definitive solution. Science fiction often imagines black holes as gateways to other universes. Could that be true? Some mathematical solutions to Einstein's equations allow structures called wormholes. A wormhole would theoretically connect distant regions of spacetime. Enter one side. Exit somewhere else. Perhaps another galaxy. Perhaps another universe. The problem is that no evidence currently shows that naturally occurring traversable wormholes exist. Even if they do, they may be unstable and collapse almost instantly. So while black holes inspire these fascinating ideas, there is currently no proof that falling into one would transport you elsewhere. As far as modern science can tell, a black hole is not a cosmic shortcut. It's a one-way trip. Let's consider a giant black hole like the one at the center of a galaxy. Sagittarius A, located at the heart of our Milky Way, contains millions of times the Sun's mass. A supermassive black hole changes the story dramatically. Because its event horizon is enormous, tidal forces at the boundary are much weaker. You could potentially cross the event horizon without immediately noticing. For a short period, you might continue observing the universe. But eventually, the tidal forces would intensify. The singularity would still await. No matter how large the black hole, current physics suggests the final destination remains the same. So what would actually happen if you fell into a black hole? From the perspective of distant observers, you'd appear to slow down and fade away near the event horizon. From your own perspective, you'd continue forward. You might cross the horizon without noticing. Eventually, powerful tidal forces would stretch and compress your body. Beyond that point, our understanding becomes uncertain. The laws of physics that describe the cosmos begin to break down. And that's what makes black holes so fascinating. They aren't merely objects in space. They're laboratories at the edge of reality itself. Places where time bends, space twists, and the deepest mysteries of the universe are waiting to be solved. The next time you look up at the night sky, remember, somewhere out there are black holes quietly shaping galaxies, bending light, and challenging everything we think we know about reality. And if you ever fell into one, you wouldn't just be taking a journey through space. you'd be taking a journey to the very limits of human knowledge. If you enjoyed this exploration of the universe, don't forget to like, subscribe, and join us for more journeys into the mysteries of space. Until next time, keep looking up.